We continue our study of self-referencing objects by now looking at what are called recursive definitions. So a recursive definition of a mathematical object usually has two parts. First, a base case, which defines the simplest objects, and then a recursive case, which defines more complicated objects in terms of the simpler ones. So the best way to understand recursive definitions is to see a few examples, which we'll present in the next several slides. So in the last couple of videos, we've been talking about recurrence relations. And recurrence relations are a recursive definition of a function. So we have a base case where we define the function for the very smallest values of n. And then we have a recursive step where we define the value of the function for larger values of n. Recursive definitions can be useful for defining certain types of sets. So you might remember that one popular way of defining a set is to do it in this way, where we tell you what the objects are and then describe succinctly the common properties shared by those objects. Now, this method of defining a set can be difficult to employ if the properties are difficult to state succinctly. So an example of such a case might be here with this thing called the Kevin Bacon set. So Kevin Bacon, if you don't know, is an actor who's been in many, many films with many different people. And what we're going to do is define a set around Kevin Bacon. So Kevin Bacon is going to be a member of this set. And then other members of these sets are going to be actors and actresses that have worked in some capacity or through some chain of films with Kevin Bacon. So that's expressed in this recursive step. So we let X be an actor or actress if for some other Y that's already in the set X, capital X, there's been a movie in which both X and Y appear, then little x now becomes a new member of capital X. So if Kevin Bacon is in X, and anyone who has been in some movie with someone in X is also in X. Okay, so here's an example given at the bottom of the slide. So I think that it's better for us to approach this example in the opposite direction from the way it's worded here on the slide. So we know that Kevin Bacon is a member of X. That's by this base case. Now, Tommy Lee Jones is an actor who appeared with Kevin Bacon in the movie JFK. So I know that Kevin Bacon is a member of X, and Tommy Lee Jones acted together with Kevin Bacon in a film. And so that means that Tommy Lee Jones is also a member of X. Now, Tommy Lee Jones acted with Harrison Ford in the movie The Fugitive. Since Tommy Lee Jones is a member of our set capital X, and Harrison Ford acted with Tommy Lee Jones in a movie, we know now that Harrison Ford is in X by our recursion. So similarly, we can use the recursion step to show that James Earl Jones is a member of X. And then finally here at the top, Arnold Schwarzenegger can be shown to be a member of X using the recursion applied to James Earl Jones. And so we can assert then that Arnold Schwarzenegger is a member of this set X. Another example of a type of object that has a recursive definition is a string. So we start with some fixed set of symbols, and we define strings in the following way. So We know that there's a string which we call the empty string, denoted by lambda. So that's a member of our collection of strings. And then we also allow any individual symbol to be a string. So one thing to notice here is that we have two base cases. And that's perfectly fine. We can have as many base cases as we like. And then for the recursion, if we have any two given strings, x and y, what we do is just simply put them together, put one next to another to form a new string. Okay, now oftentimes the symbols we use are just 0 and 1, in which case our strings are called binary strings. Okay, so for example, if we're going to let these be the symbols, just 0 and 1, then I can form the string 0 just by B2, and I can form the string 1 by B2. I know both of those are strings. And then the string 0, 1 comes from applying the recursion R to those existing strings. Now, we can have strings of all kinds of different lengths, this object is also a binary string. And it can be formed from the simplest things, the 0 and the 1, which are strings, and then concatenation. We can also define the reverse of a string using a recursive definition process. So the very first thing we do in the base case is define the reverse of the empty string. So the reverse of the empty string is just going to be itself. Now for the recursion, let's suppose now that we have a string with one or more symbols. And what we're going to do is write that string as another string R together with the very last symbol A that's in the string. Now, if the string consists just of a single symbol, then the string R at the front is going to be the empty string. So in this instance, if we want the reverse of string S, that's the same as the reverse of string RA, because RA is equal to S. And then we just move the A to the opposite side and concatenate that with the reverse of the smaller string R. So here at the bottom of the slide, we have an example. So we have this string PIT that we're going to reverse. So PIT is a non-empty string. The last symbol in the string is T. And so what we're going to do is pull the T around, put it in front, and then concatenate that with the reverse of this smaller string, PI. So we will now need to find the reverse of the string PI. Well, according to the recursion again, remember PI ends with I, so we bring the I out in front of the string PI and then take the reverse of P. So P we can write as lambda P. So we take the P out in front again using the recursion, and then we just have lambda, the reverse of lambda. But the reverse of lambda is just itself, and lambda is the empty string, so we just remove it. And so we get what we would recognize as the reverse of the string PIT. Another example of a recursively defined object is what's called a line map. So what you do is you start with a blank rectangle. Okay, that is the base case. It's the simplest object. And then to create other line maps, what you do is you insert lines across the rectangle. So that new object that I get is another line map that I formed using the recursion. And now I know that this given object this object I've just created is a line map. I can create another more complicated line map by drawing another line. So there's a new line map that I have, again, obtained by applying R. And then eventually you get objects or line maps that look like this picture at the bottom of the slide, and I can make, again, another more complicated line map from this one by inserting a line of my choice across the rectangle. So how does one write recursive definitions? Generally speaking, what you do is use the base case to describe the simplest possible objects in the set, or whatever it is you're trying to define. And then the recursion or recursions are used to describe the more complicated objects in terms of the simpler ones. So here's an example of forming a recursive definition. So let's suppose we start browsing the internet at some specific page P, and we're going to let X be the set of all pages we can reach by following links starting at P. So we want to have a recursive definition of the set X. So at this point, maybe you would want to pause the video and see if you can produce a recursive definition of the set X. Okay, well, now that you're back, you might have realized that this set X is very much like the Kevin Bacon set, right? Where our beginning page P plays the role of Kevin Bacon. Right, so our simplest object is the page P itself. And to get more complicated objects, well, if Y is a member of our set already that we can reach from P, and X is some page that we can reach from Y, then X should also be reachable from P, and therefore X is in our set capital X. So again, I encourage you to compare this example to the Kevin Bacon example we had a little bit earlier in the video. Okay, another object or set of objects that we can define recursively is the collection of odd natural numbers. So again, maybe it's a good idea to pause the video, go away, and see if you can do this definition recursively. Okay, now that you're back, maybe you did this, right? So for your base case for the odd numbers, the simplest odd number seems to be 1. And now how do I get other odd natural numbers? Well, I could get 3 from 1 by adding 2. I could get 5 from 3 by adding 2. And so maybe our recursion is this, that if X is already an odd number, we can get another odd number by adding 2 to X. Now, another set of objects that can be defined recursively is the set of binary trees. So in this instance, we're going to have 2 base cases. So first, we're going to let the empty tree be a binary tree. And then we will also let a single vertex, just a single node, be a binary tree. Now, how do we form new binary trees from existing binary trees? So let's suppose we have 2 existing binary trees, T1 and T2. And I want to now make a new and more complicated binary tree. So what I do is I go and I find the top vertex of each of these existing binary trees, and then I form a new vertex R above those 2 and connect R to both of the top vertices in the existing binary trees using these edges. Then I have formed a new and more complicated binary tree. Now, one thing to keep in mind is that it's possible that one or both of these existing binary trees is empty. So if it's empty, then there is no top node, and so we would not form an edge in those cases. So for example, let's take two existing binary trees and put them together. Like, let's suppose we have this tree as being T1 and maybe this tree as being T2. If I use the recursion, I form a new vertex R up here and I just simply join them. And that's my new binary tree. So our final example is the Koch snowflake, which is an interesting fractal type figure. And the way we start, our base case towards forming the shape, is to form an equilateral triangle. So K1 is that figure. And then for larger values of n, we form new figures. And the way we do it is through this recursion. So Kn is formed from k sub n minus 1 by taking every single segment in k sub n minus 1 that looks like that and replacing it with a segment that looks like this where we have a tent in the middle. So if in kn minus 1 we have a shape like that or a segment like that, then in kn that segment is replaced by this new object. So here we see an example of the base case and the recursion in action. So remember, our base case is just the equilateral triangle. Now, when we apply the recursion to the base case, what do we do? Well, we take our equilateral triangle and we look at each line segment, which is a side of the triangle, and we replace that line segment with this tent-shaped path. And you can see that if you do that to every side, you wind up with this shape, K2. Now, K2 itself is made up of a bunch of line segments, right? So for instance, let's focus on this one right here. That line segment is part of what makes K2. Now, to make K3, we take every single line segment, including the one that I've circled. So here it is in K3. We take that line segment and replace it by the tent shape. Okay, and then we continue. And we can continue as long as we like. And ultimately, we get these very interesting and beautiful shapes that look like snowflakes.